Every frontier language model has a fixed physical limit on how many tokens it can process at once. But even before hitting that hard ceiling, it suffers from context rot. As the prompt grows, its ability to retrieve information begins to fracture. The standard industry fix is compaction, summarizing the text once the window fills up. This fails on information-dense tasks because it assumes early details can safely be forgotten. If the final answer requires a specific fact from the first paragraph, compaction often destroys the exact data needed for a correct response. Standard retrieval, or RAG, also struggles here. Chunking a corpus into isolated pieces works for simple lookups, but it fails when a query requires multi-hop reasoning across thousands of interconnected documents. These failures stem from a specific architectural choice: the insistence on feeding massive token counts directly into the neural network's attention mechanism. A recursive language model, or RLM, is an inference-time scaffold surrounding a standard base model. It leaves the underlying neural network architecture entirely unchanged. Instead of pushing millions of tokens into the network, the scaffold blocks the text entirely. The prompt drops into an external Python REPL environment. The root model never reads it, seeing only constant-size metadata passed through the scaffold. By treating the prompt as an external variable, the system separates the size of the human problem from the network's fixed attention span. Algorithm 1 achieves unbounded input without context pollution by following a specific execution loop. It starts by loading the prompt string into the REPL state, then seeds the root model's history solely with that state's metadata. This metadata node contains no semantic text. It is purely dimensional data. The model knows the shape and location of the prompt, but not its contents. From here, the root model generates a block of code. Because it only has metadata, this code is specifically designed to peek at or slice the external prompt variable. That code passes into the REPL and executes. It updates the environment state and generates standard output. To prevent the root model's window from filling up, the output is forcibly truncated. Only the metadata of the execution result loops back into the history log. This loop repeats. The model writes code, probes the variables, and receives metadata summaries until it assigns the final answer to a specific variable labeled final. This truncation discipline forces the model to rely on persistent REPL variables and recursive sub-calls to manage information. The root model's own context window remains stable, regardless of the initial input size. It is easy to assume this is identical to a standard CodeAct agent equipped with a sub-call tool. However, standard coding agents still hit window limits when processing 10 million token workloads. This architectural comparison reveals why standard agents fail. On the left, the direct loading approach drops the prompt straight into the history log. On the right is the first RLM design choice, providing only a symbolic handle to the prompt. By refusing to load the actual text, the right side automatically avoids the base model's window limits, which removes the need for compaction. The second deviation is the output method. On the left, the agent uses a single finish action, hitting a hard ceiling on token generation. On the right, the RLM produces its answer into a persistent REPL variable. Building the answer inside the REPL allows the system to solve tasks where the correct answer is physically larger than the model's maximum allowed output tokens. Finally, standard agents rely on verbalized sub-calls, narrating each delegation one at a time. The third RLM design choice enables symbolic recursion. The REPL executes programmatic loops that can spawn thousands of parallel sub-calls over slices of the prompt. Standard agents are bounded by how many delegations they can describe before the context window fills. RLMs move that limit to the execution logic itself. This programmatic looping allows the semantic work to scale at big omega of p, or even p squared. By writing a script that iterates through every pair of entries in the external variable, the system performs a number of reasoning steps that would physically exceed the history log of any standard model. Despite this scale at the system level, the individual leaf subcalls remain standard, general-purpose LLM requests operating on short, manageable strings. Symbolic recursion moves the primary system bottleneck away from neural token limits and toward the limits of programmatic execution. Regardless of the task, RLM rollouts converge on a predictable execution grammar inside the REPL loop. The first pattern is the probe. Before doing any expensive neural work, The root model writes regex filtering code to search and slice the massive prompt variable. Next is the decompose pattern. The model splits the narrowed prompt into distinct subproblems and routes them into recursive sub-calls for analysis. Finally, the stitch pattern. On long output tasks, the system concatenates the sublotl outputs back together inside the REPL to construct the final answer. The primary driver of quality is the first decomposition attempt. If the model slices the problem intelligently on turn 1, it succeeds. Providing even a single unrelated in-context trajectory example improves this first cut. The limiting factor for specific models, like Quen-Coder, is the syntax error rate. At higher recursion depths, early coding mistakes propagate down the chain of subcalls, leading to a failure of the entire trajectory. The REPL allows the model to substitute expensive neural attention with cheap algorithmic search, applying heavy semantic processing only when strictly necessary. This architecture works for massive inputs, but it also applies to dense reasoning chains, where the input text is small, but the required logic is deep. On the long-caught-many benchmark, models often fail because subproblems are highly interdependent. Making one mistake early on breaks the final calculation. To solve this, researchers guide the RLM using a 5-step hint structure. This graph represents the underlying directed acyclic graph, or DAG, of the problem. Step 1 is the plan. A single subcall extracts the problem's JSON structure, mapping the dependencies without attempting to solve them. Step 2 is the solve layer. The system executes a parallel batch of LLM calls, solving the first layer of nodes that have all their dependencies met. Step 3 enforces verification. Every node's answer must be independently verified by a secondary check before that data propagates further up the graph. Steps 4 and 5 resolve cyclical dependencies and assemble the verified pieces into the final answer purely by dictionary lookup. There is a strict red flag in the system prompt. The RLM is forbidden from computing math or logic directly in Python. Python must only be used to orchestrate the graph and manage dictionary lookups. All actual semantic work is forced into isolated, verifiable LLM batch windows. Instead of relying on sequential token generation, the scaffold uses the model to orchestrate a graph of independent subcalls for unbounded reasoning. Engineering requires a reality check. Do these recursive programmatic loops cause inference costs to explode? This cost distribution chart shows a counterintuitive reality. The marker on the right is the median cost of feeding a massive prompt into a base model. The marker on the left is the RLM. The median RLM run costs less. Instead of scaling purely by input size, RLM inference cost scales proportionately to the specific algorithmic complexity of the task itself. However, the average mean cost diverges from the median. This is driven by a long tail of struggling, high-cost trajectories. The primary cost killer is subcall spam. This behavioral loop wastes thousands of sequential API calls on a single task without arriving at an answer. The solution to these runaway loops is distillation. By post-training smaller models like the 8 billion parameter RLM Quen-3, researchers optimize the model for REPL decision-making and subcall timing. Mitigating these behavioral loops is what makes these specialized orchestrator models viable at this scale. The RLM framework moves the prompt entirely out of the neural context window and into a manageable external environment. It replaces verbal delegation with symbolic, programmatic loops that can search, verify, and aggregate data. This is an inference-time scaffold that can be applied to existing models rather than a new architecture. By treating a language model as a semantic function within a larger programmatic loop, the system decouples human problem size from neural network constraints.